Hi, everyone. My talk today will be about a problem that we worked on that involved OpenStreetMap and GIS. Just as an introduction, my name is Orden. I work as a geospatial analyst at a consultancy in the Philippines called Thinking Machines. Our company helps our clients make better data-driven decisions through business intelligence, data warehousing, and data science. My role is to provide domain expertise with GIS, and I do that using spatial analysis and web mapping. The slides for this talk can be found in this bit.ly link shown here on the screen. I'm excited to get a chance to talk about a problem that we worked on today. And this problem is about finding where the unmapped areas are. And I'll be talking about the method and the tools that we used. As some of you might know, there's a map of the world called OpenStreetMap or OSM. For those who aren't familiar, I guess some of you might be asking, what's the difference between this and Google Maps? There's basically three characteristics of OSM that's important. It's free, it's editable, and the data is available to anyone. And we can go on and on about the differences of the two maps. But for this talk, the most important thing to remember is the fact that OSM is editable. There's a whole community of people who contribute to OSM, similar to Wikipedia. OSM is very comprehensive, and there's actually a lot of data on there. There's data about hospitals, schools, malls, roads, buildings, mountains, rivers, and plenty of others. There's a lot of data, and because of that, there are now a lot of important uses for it. For example, different organizations use OSM to plan relief efforts during disasters and other crises. In the past, OSM was used to help with the response to the 2010 earthquake in Haiti, the 2014 Typhoon Haiyan in the Philippines, and the Ebola outbreaks in Africa. On the public service side, I've met some civil servants from the Philippines who have said that they use OSM to improve public services in their local government. We have to remember, though, that there's only a limited number of volunteers who can map and contribute to OSM, and they can only do so much. There are still a lot of areas where there are no maps, and we believe that these unmapped areas are a problem, especially if there are people there. Because whenever there's disasters or crises, these people will be neglected. The reason is because no one knows where they live, no one knows where their houses are. And since no one knows where they are, the organizations giving out aid won't be able to reach out to them and give them what they need. So there's actually a need to map the unmapped areas in the Philippines and all around the world, actually. There's an active community of people who contribute to OSM, and we wanted to help them by, number one, showing where the unmapped areas are, and number two, measuring how much needs to be mapped. What we're measuring is the completeness of the data. We decided to focus on measuring the completeness for building footprints. We did some digging and we found out that there's a previous work where they measured the completeness of building footprints using GIS and ML or machine learning. And this is where our work comes in. We present a methodology that uses GIS solely, and this is simpler to implement and still provides insights regarding unmapped areas. Our proposed methodology has 3 steps. I'll explain each step so that it's easier to understand. The first step is vectorizing the settlement layer. A settlement layer is an image that shows areas in the world where people live. I included the settlement layer here at the right side of the screen in the image so that you can see what it looks like. This settlement layer came from the Facebook Data for Good website, but it's also available in Humanitarian Data Exchange. So you can go to this link in the lower left to download it. The data of a settlement layer is these black things that you see. So these are actually the pixels of the image. Each black pixel that you see is an area with a population value. In other words, each pixel shows where people live. That's the explanation for the settlement layer. The explanation for vectorizing is that it's a processing step. It's a pre-processing step that involves turning the image into a different data type. We do this so that we can perform the next step, which is the spatial join. The second step is performing a spatial join using the settlement layer in the OSM buildings. A spatial join is a way to join two datasets using their spatial relationship as a join key. So this is similar to what you would do in SQL, where you do like a join with two columns. But with a spatial join, you're using the spatial relationship as the join key instead. So the spatial relationship that we're using is called the intersection, and it's just like what it sounds. Basically, what this step does is it finds the intersection of the settlement layer and the OSM buildings. It finds the intersection of those two. As you can see in the image here on the right side, there are black pixels, and these are the settlement layers that we've seen earlier. And there are also green polygons, so these are the OSM buildings. The output of this step is the intersection of the settlement layer and the OSM buildings. I'll go to the next slide to show what the output looks like. So here's the output. Let me go back. And here it is again. The output shows which areas are mapped. That's the one in blue. And which areas are unmapped. That's the one in orange. And this output is then used for the next step, which is calculating the percentage completeness. The formula here is super simple. It's just arithmetic based on the number of pixels that intersect with the OSM buildings. Those are the three steps in the methodology. The main assumption behind the method is that the settlement layers can be used as a proxy ground truth for buildings, because settlement layers are taken from satellite images of built-up areas. So these built-up areas have population in them, and by that logic, you can use that as a proxy ground truth for buildings. Well, we made a web map to show the output for the Philippines, and here's like a GIF of it. So orange means that it's unmapped, blue means that it is mapped. One cool thing that we did is to show a button that will link you to OpenStreetMap if you want to contribute. So you can check it out here in the link in the left, mapthegap.thinkingmachines. Try it out later and see it for yourself. You can zoom in and check which areas are mapped and unmapped. We also wrote a blog post about this so that we could share our work with others. And what's cool is that the Mapbox community team reached out to us and they asked us to do it for Madagascar. The context of this was to improve women's health. And you can check out both the website, both the blog post and the website with the map here in the links below. So that's it for the outputs. And I mentioned earlier that there's a previous work that measured data completeness for OSM building footprints. The previous work was done by a group of researchers from a company called Azavea, and they did this in partnership with Development Seed. Development Seed is a mapping company that works with nonprofits, and they measure data completeness in order to understand the progress and completeness of malaria campaigns in Africa. You can check out the repository on GitHub to find out more. There are like three main differences with their method and our method. First is that they used WorldTop instead of the Facebook High Resolution Settlement Layer, or HRSL. Just to clarify, both settlement layers used machine learning to detect built-up areas from satellite images. The difference is that WorldTop has a lower resolution, which is 100 meters per pixel, as compared to HRSL, which is 30 meters per pixel. HRSL was only available for a few countries in Africa during the time that the Development Seed and Azavea did their study. When we did our study, it was already available for more countries, and we believed that it would be interesting and useful to use HRSL instead of WorldTop. Second difference is they rasterized the buildings instead of vectorizing the settlement layer. The settlement layer they used had a resolution of 100 meters, and they were concerned with the resolution difference with the buildings. On the other hand, the resolution of the settlement layer we used was 30 meters, and the resolution difference was not as big of an issue. The third difference is that they used machine learning to predict the data completeness. Both methodologies actually used GIS. Both methodologies got the intersection of the settlement layer with the OSM buildings. However, they proceeded to give the outputs of the GIS step into a linear regression model. In contrast, we just did arithmetic. And the advantage of using this is that it's simpler to implement and it still provides insights regarding where unmapped areas are. Now we get to the results. Based on the building footprints from January 2020, the percentage completeness is 32.75% for the Philippines and 10.89% for Madagascar. This indicates that there are still a lot of unmapped areas in these two countries. Just some notes. Number one, the human settlement layer is dated June 2019 for the Philippines and October 2018 for Madagascar. So this might mean that the percentage completeness might actually be lower or higher because the data for the settlement layer was from a different date for the data for the buildings. And another note, number two, as mentioned earlier, percentage completeness is calculated using the arithmetic of mapped pixels and unmapped pixels. And we'd like to note that the percentage completeness is a correlated metric for building footprint completeness, but it's only a proxy. Because if you remember the image earlier, the pixels, they don't have a one-to-one correspondence with building footprints. There are times where there are multiple building footprints in a single pixel and vice versa. And we did some analysis. This is mostly for the Philippines. For the Philippines, we did some analysis on the relationship between data completeness and urbanization. And we found that most of the unmapped areas are rural. And this kind of makes sense since most of the Philippines is rural. So a large number of level 4 admin boundaries have a percentage completeness of less than 10% for rural areas. So we got the results of the percentage completeness for the level 4 admin boundary. And we decided to aggregate to a larger admin boundary so that we could get more insights. So we aggregated to the level 3 admin boundary, which is the municipality level. We plotted the rural percentage completeness versus the urban percentage completeness at the municipality level. Here we see that the municipalities appear to group together into two categories. One's barely mapped, that's the one on the lower left, and one's thoroughly mapped, that's the one on the upper right. We believe that this is revealing of the way the OSM community maps areas. So a possible explanation is that the OSM community focuses on thoroughly mapping certain municipalities first, like the high population ones, the ones that where they live and so on. And after they mapped all of that municipality, that's when they map the other municipalities. So this could be a case of focusing on one area first. That's why there's a lot of unmapped areas still. Of course, this is all to say that there still needs to be more volunteers to increase the number of data that's contributed. And again, we did an analysis this time for the data completeness and poverty. So this is still for the Philippines. We took poverty incidence data from 2015 for the municipality level from the national statistics. So interestingly, poverty incidence is not correlated with data completeness. Complete or incomplete OSM data in an area is not an indicator of wealth or poverty. We'd like to note, though, that a caveat of this analysis is that the poverty data is from 2015 and the percentage completeness data is for 2020. So a reason why it might not be correlated is because the data is from different times. So it could be that now an area is fully mapped, the poverty there is less high, and so on. We also created a bivariate choropleth map, and this is just to visually look at the poverty incidence and the data completeness as two things together. Here we see that there's kind of a spatial trend in the poverty incidence. So for example, in the northern part of the Philippines, it's mostly blue. So this means that there's low poverty there. And then in the southern part of the Philippines, it's Mostly red means that there's a high poverty incidence there. In terms of data completeness, though, there's no apparent spatial trend. This is kind of in line with the graph shown earlier. But we do recommend doing further spatial analysis on this, since it does look like if you look at one area locally, like for example, if you just look at the northern Philippines, there seems to be a trend. And if you just look at the southern Philippines, there also seems to be a trend. So that's with the results in the analysis, and I'd like to double back on the implementation. So initially, the implementation is done in QGIS. And for those who aren't familiar, QGIS is a software for doing GIS stuff, and it has like a user interface. So you can do all of your geography work and all of your geospatial data. You analyze all of it there and show it there. And it's easy to prototype stuff there, and whatever you can think of, you can also work with it there. But of course, this is what we used at first because we just wanted to create a web map and we wanted to write a blog post. And this is just for the Philippines. But over time, more people, specifically the humanitarian OpenStreetMap team, asked us if it would be possible to update the results more frequently. And we also started looking at the possibility of getting the results for all of the countries that have HRSL data. Basically, we had to consider the reproducibility and the scalability of the implementation. We looked into ways to automate workflows in QGIS, and we did the workflow builder tool and the QGIS API. We had to consider that the scalability and the reproducibility, though. And we realized that QGIS is not fit for our use case. It's not scalable because you're just doing your data processing in one computer, and it's kind of hard to parallelize as well. It's also not reproducible. It's not easily reproducible, especially if the person who's doing the thing is not trained in the use of GIS software and stuff. So that's why we decided to migrate our workflow to GeoPandas and Raster.io. You can check out the source code on GitHub. You can check it here. Just check the link in the lower left. And when we did migrate it, we were able to improve our workflow because, number one, we were able to migrate to the cloud and increase compute resources. So now we're able to scale up and get the results very, very quickly. Number two is all of our analysis, our pre-processing, all of this is now in Python. So it's easier for us to work on it, and it's easier for us to collaborate on it with others as well. So we can work with our different engineers and data scientists. I think another useful thing with migrating to Python is improving the shareability of the work. So I think that GIS is going to be more interdisciplinary, and by putting our work out in Python, we're able to reach people outside the GIS community. So we're also able to work with like researchers, software engineers, and data scientists. Just to close, I'd like to mention the recommendations, basically like what the next steps for this research is. So the first is to get like the percentage completeness for all countries that have HRSL data. That data is available in Humanitarian Data Exchange, so you can check it out in this link in the lower left. It's under the Facebook organization in HDX. The second thing that we need to do is to set up a data pipeline to get frequently updated results. So we already have code for the methodology, and what the data pipeline will do is to make sure that the methodology will run frequently and that the methodology will give the most recent data so that we can update the map right away. So it's more of like an engineering thing that we have to tackle. And we're very excited to work on this as well, since we do believe that it will have a big impact. That's it for the talk. I'd just like to give some special thanks to the Philippine OSM community for all of their contributions to the map. We encourage everyone to try out the method and see the results for your own countries. And I'm sure that if you share the results with your local OSM community, they would be very appreciative. We'd also like to thank Hot OSM. So this work is driven by our desire to help out the OSM community, and Hot OSM, in their goal to map the entire Philippines, has been very, very helpful, and we're glad to help them in whatever way we can. We'd also like to thank everyone at Thinking Machines, all of our colleagues, for giving us the support we need to work on this and for giving us valuable feedback for this work and this presentation. Thank you all for listening. You can check out our work at GitHub, and you can check out the slides from this talk in this bit.ly link. So I'll now be taking questions, but if you'd like to get in touch after this talk, you can email me at rd@thinkingmachines. Thank you so much.